Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's our great pleasure to have Professor Keith Ross to come here and give us a talk again on the advances in the peer-to-peer live streaming. Professor Ross is a chair professor in the CS department of Polytechnical Institute of NYU. That's basically Brooklyn Poly merged with NYU. I believe you are also the current department head of CS department. Professor Ross has worked on a large range of topics, including peer-to-peer networking, internet measurement, video streaming, web caching, multi-service loss network, etc. He authored the popular books, Computer Networks, a top-down approach featuring internet that many of us have read. And this book is already in its 5th edition, being translated into 12 languages, I believe. And is the most popular book nationally and internationally for the CS department on networking aspect. Professor Ross is an IEEE fellow and serves as associate editor for IEEE Transaction on Networking and is PC chairs of many conferences. And today he will talk about their new research work on peer-to-peer video streaming, including view upload decoupling and theoretical analysis of how view upload decoupling is going to help peer-to-peer live streaming. Without further ado, let's hear what Professor Ross has to say.
Thank you very much, Jin. Also, thank you very much for inviting me to Microsoft once again this summer to MSR. It's always a great pleasure to be here. It's a very stimulating environment. It's very. It's
our pleasure.
Yeah. So it's something that I enjoy every year. It's like having every year I come here, it's like having a little mini sabbatical. It's very pleasant. So what I want to do is talk about 2 recent papers that we've completed in the area of P2P live video streaming, and both of them appeared at Infocom in Rio de Janeiro this past spring. The first one appeared in the mini conference, and the second one appeared in the regular conference, and the second one also, much to our surprise, also won the Best Paper Award this year at Infocom. So that's what we're going to talk about today. They're 2 very related papers. And so it makes for one coherent presentation, I hope. So first, just a very brief overview of P2P video streaming. We have a lot of experts in this room here on P2P video streaming, so I don't want to spend too much time. Some of the leading, we have right here in this room, some of the leading researchers in the field. And so we'll go through that quickly, and then talk about video uploading. View upload decoupling, that's VUD, which stands for view upload decoupling, and then queuing models for P2P streaming, which apply both to traditional designs of P2P live streaming and also to VUD as well. So peer-assisted video streaming, for those that you have not seen this before, basic idea is peers redistribute video chunks to each other. Similar to BitTorrent. It's really been inspired by the BitTorrent design. The idea is to use the peer upload capacity and reduce the load on the server. That's the main reason why you're doing this P2P video streaming is, in fact, to reduce the load on the server and use the upload capacity of the peers to do the work for you. So the basic situation is as follows. You have a single video, a live video that a server wants to transmit to a large number of peers, maybe 1,000 or more. Here's just a picture of 6. The server sends video chunks to some of those peers, in this case peers 2, 6, and 5, and then the peers redistribute the chunks among themselves. So again, the idea is the peers are assisting the video distribution of the the video, the live video channel. There are many large-scale deployments today of this. This concept has been demonstrated to work quite well. There's a number of them: Cool Streaming, PP Stream, PP Live. So let's just say a few words about them. Just a historical thing. Cool Streaming was the first one. I believe it was developed at the University of Hong Kong of Science and Technology. So that was sort of the first one to show that this concept can actually work. It had over 1 million users. More recently, there's a number of other companies involved. PP Live is one example. It has today over 85 million users. It has over 800 channels available. Another very popular one, which perhaps is the most popular now, at least my postdoc tells me that, is PP Stream. And that has over 350 million installations and 12 million active users every day. So it's really on the order of something like Skype with 12 million active users every day, and has thousands of channels as well. So what are some of the common features of the live streaming systems? These companies I just talked about, they offer both live and on-demand streaming. We're focusing here today on live streaming. What are some of the common features? One major feature is that they have multiple channels. And that's something we really want to look at carefully in this talk today. And so in addition to there being peer churn, there is channel churn. That is, users tend to jump from one channel to another. Most of the literature in P2P has focused on system churn, just on the actual people bringing their laptops and starting up the P2P application and then turning off the application. But there's actually another type of churn that happens at a much faster time scale than traditional peer churn, and that's channel churn. And so we'll come back to that, but that's something that we're very concerned about in this talk here. Another thing is, of course, that there are heterogeneous streaming rates. The different channels are being offered at different rates, some at high HDTV rates, some at VCR quality rates, etc. Of course, the channels have heterogeneous popularity. Some channels are extremely popular with tens of thousands simultaneous users, and other channels have maybe just a handful of small number of users, 3, 4 users watching it simultaneously. And all of the existing systems, PP Stream, PP Live, etc., they use today what we refer to as an isolated channel design, or ISO. And in this design, in the traditional design that's going on now, is a viewer only redistributes a channel that it's watching. So if a viewer is watching the World Cup soccer game, then it will redistribute the World Cup soccer game. It will not redistribute something else, like a tennis match or something, or Desperate Housewives or whatever. It only redistributes what it's watching. This is the classical design. This is similar to the BitTorrent philosophy. In BitTorrent, right, when you're downloading a file, that same file that you're downloading, you're redistributing it. You're not redistributing some other file. So what are some of the problems? If we look at these, even though they're very successful with tens of millions of simultaneous users, these systems still have some performance problems. So there's room here for improvement, so room here for a competitor to come onto the market and try to build a better system that overcomes these problems. One of the bigger problems that we've observed is that there is generally a large channel switching delay. Now, as we know, like when we watch TV at home, which comes from cable or satellite, the switching delay from one channel to the other is on the order of 1 or 2 seconds typically. But in these systems, the switching delay is much longer. It's on the order of 10 to 60 seconds. And so these systems still are not really, are still a while to go to really to approach the switching delay that we have in the systems that we're used to. Another problem is that there's often a large playback delay. The playback delay is defined from when, for example, if you're watching a soccer game, from when the goal actually occurs in real time until it appears on your screen. So the playback delay in these systems can be from 5, even 60 seconds long. So what that means is that the goal actually, when you see the goal, it actually occurred a minute earlier. So you might hear your neighbors cheering and screaming, 30, 40 seconds before you actually see the goal occur. Okay, so that's one problem. Another thing that's been observed is that you have sometimes poor performance for small channels. So if the channel is very small with just 3 or 4 simultaneous users, you have a lot of those channels, the performance may be erratic and not very good. You have a similar kind of phenomenon in BitTorrent as well. Generally speaking, in BitTorrent, you get better download rates when you join a channel that has a larger number of users than when you join a swarm that has a small number of users. Now, what are the root causes of these 3 problems here? There are really 2 root causes. One, we argue, is channel churn, that we have these users that are rapidly jumping around from one channel to the next, and because of that, we're going to show some slides here, but they're impacting the distribution swarms in a very negative way. The second is resource imbalance. That is to say that there's this notion of a resource index in these P2P live streaming systems, and each channel has its own resource index, and it can be very different from one channel to the next, and that causes problems as well. So we're going to elaborate on that in a few seconds. So let's look at the channel churn problem in the ISO design. So here we have a very simple situation where there's only 2 channels, channel 1 and channel 2. And so channel 1 might be World Cup soccer game, channel 2 might be Desperate Housewives, for example. And we have viewers in channel 1 and we have viewers in channel 2. They're each getting their video chunks and redistributing the video chunks to each other. Everyone's happy. But now we have some channel churn. So viewers 3 and 1 decide all of a sudden that they want to watch channel 2, and viewers C, F all of a sudden decide they want to watch channel 1. So what's going to happen then? Basically, that's going to cause is the following. Is now all of a sudden, for example, peer 4, who previously was getting chunks from 1 through 6, is no longer getting chunks from peers 3 and 1. So it's missing these chunks. Now it has fewer places to go to get chunks. So that's going to potentially cause problems. There can be now we're setting up for a situation for missed chunks. We're not going to get all the chunks that we need, and also we probably need to find more. We may need to find other peers, other sources of data where we can get chunks from. So that's going to take some time for say peer 4 to find that. And same thing when C and F come here and join, because now it's not a very stable system. Peers are leaving and going. It's going to take a longer time for C and F to find peers, stable peers that can supply it chunks. So that is going to impact the performance of the system. Now, so that's the first problem. That was like the channel switching problem. The other problem is the resource imbalance that we mentioned. And so to describe resource imbalance, we need to introduce this concept here, the instantaneous resource index. And many people have used that this measure in analyzing video streaming systems over the years. We're not the first to introduce this, but it's an important measure. And basically what it is if you have end users watching a channel, this is for a particular channel, and the rate of the channel is R, this is the total demand for that channel. It's N times R. That's how many bits that need to be uploaded to all the end users. And this here is the upload capacity that's brought by the end users. This is the upload capacity of the server and the upload capacity of the end users. This is the aggregate upload capacity. So in order for the system, the channel to function properly, the total upload capacity needs to exceed the demand, N times R. So the supply needs to exceed the demand. If this value sigma here is less than 1, then you're going to have trouble. Then the supply cannot meet the demand. So we're going to come back to this is an important ratio here. It is this resource index, and we're going to come back to it a few times during this talk. Now the problem, one thing is that when you have multiple channels, this resource index, which is also a function of time because things are changing, the number of peers in a channel are changing, the resource index from one channel to the next is typically very different. Some channels may have a very high resource index, others very low. There's potentially a great imbalance when you're using this isolated design. So that's another thing that we're going to try to solve. Not only try to solve the channel switching problem, but also this resource index imbalance across channels. So that gets into this new design that we refer to as VUD, or view upload decoupling. And so let's talk about that. So here's the new design. So again, it's just an example here. We have two channels to show for illustrative purposes. And what we're going to do is first we're going to break each channel into a certain number of substreams. And the reason we're doing this is because I'm going to come back to this a little later, but this VUD design introduces new overhead. And in order to reduce the overhead, we use this substreaming. So we'll come back to that. So we're going to break each channel into a substream.
Just a quick question.
Sure.
So for example, so right now you're just doing this way. So let me just propose a very simple solution, see if it works or not. Just very simple one.
Okay.
And so from your example, you see 1, 3 left,
Uh-huh.
the right-hand side. Now somehow there are holes. They cannot be filled for a while.
Right.
That cause problem for the other three guys. A simple solution, instead of using this one, would be, how about you ask 1 and 3 to stay a little bit, even though they are switching to another channel.
Right.
They can still supply
Right.
to the other viewers until they have used up. Essentially, they become useless.
Uh-huh.
Once they become, I do have local buffers. I just wait for a little bit longer, meaning transition oftentimes you can overlap, right?
Mm-hmm.
So system, you want to maintain consistency. I switch to another channel, but I wanted to continue supply, say, for 5 minutes or whatever. Algorithm, fixed time, supply until 5 more minutes or do some other thing else. Would that solve problems instead of using this more fancier version?
I don't know if that's, this is going to be that. I guess this is fancier than that. That is something a little bit along the lines of this in some sense, but would that solve the problem as well? Those guys are still there.
Stay 5 more minutes. Don't leave.
5 more minutes, but here though we have a lot of users that are jumping around every 10 seconds. You've got to keep in mind that we find that the average 70% of the holding times in a study that's been given by at Telefonica is less than 10 seconds you're staying in there. So you're going to say, the guy's going to go in there for 10 seconds, and you're going to ask him to stay for another 5 minutes.
Okay. 5 minutes, that's a simple rule that become multiple rules, for example, until you become useless. Meaning, all my neighbors no longer need my data, so therefore, you can go now. Now the obligation is gone because I'm just throwing in some. If the diversion, just asking if that's a simpler solution.
I think, I don't know, I guess, I just have to think about it more, but gut feeling is that might make sense. If users really were staying there for a long time, then why not have them just stay for another 10 seconds? But here, they're really jumping around quite a bit here. So,
my thought here is this. Usually in a peer-to-peer system such like this, the most important resource is bandwidth, right?
Yes.
Rather than the cache. So I mean, the fact that you may hold a piece of video may not actually be that worthwhile, rather than the resource you can.
There's also block availability. Well, yeah, I guess probably should
see we may want to see that piece.
So now what we're going to do is we are going to, since we have all these peers that are jumping around all the time, we're going to say, if you're one of those peers, persons, one of those users, we're going to say, we're going to put you in a fixed channel, and your job now is to distribute that channel no matter what you're viewing. So this is why we're decoupling. It's called video upload decoupling. What you're uploading is going to be independent of what you're viewing. So that's the basic idea. So here, so we have, what we're going to do is organize the peers. So these 3 peers here are assigned to substream 1. And their job, no matter what they're watching, they just always redistribute substream 1, as long as they're in the system. This is crude form. And so, and these guys here, and then so we send substream, channel substream 1, and they redistribute it among each other. Usually there may be a bigger group here, But in the end, each one of these guys gets all of substream 1, has all the chunks of substream 1. And let's come back here. These guys here redistribute, get substream 2. And going over here, these guys get channel 2 substream 1, and these guys redistribute substream 2 of channel 2. So these guys are just sort of fixed here, and they serve as redistribution groups. And then if these guys here, suppose all these peers, 1, 2, 3, 4, 6, want to watch channel 1, then what they need to do is get substream 1 from this group here, and they need to get substream 2 from this group over here. And so, so what that means here now is that each peer, like for example peer 1, it's downloading these 2 substreams because it's viewing these 2 substreams, but it's also getting a substream here, this orange one, that's not even interested in whatsoever. This might be, again, he might be watching World Cup football. This might correspond to Desperate Housewives. He's downloading Desperate Housewives even though he doesn't want it. Okay, but that's part of the design here. Okay. Yeah, well, yeah, we're going to get into that. Okay, so there's an overhead issue. There's no doubt about it. There's an overhead issue. So, putting aside the overhead issue, let's suppose now that that all of a sudden we have some switching just like before. So C and F move over to channel 1. They start watching channel 1, and 1 and 3 start watching channel 2. When these people switch channels, so they're switching back and forth, these distribution groups remain constant. Nothing happens in the distribution groups. So when C comes over here, it's relatively easy for C to find the substreams that it needs because these guys are constant. They're always there. They're always providing the video. We don't have to search too hard, ask a lot of peers, do you have the chunks? Those guys have the chunks. And so that will help us reduce the switching delay significantly. Okay. So the other thing we can do here is we have the possibility of dimensioning these substream groups and in some kind of sophisticated manner if we want. We can now, just like in traditional teletraffic engineering, we can go ahead and start to try to dimension these groups to suit the demand. So there's going to be a demand for each substream, and we can try to dimension these groups to match the demand for the substreams. Okay, and that way we're going to be able to get to this here is this cross-channel provisioning. Now, since we could dimension each of these substream groups, we can dimension them in a way that the resource index, hopefully, is basically balanced. Before we said that the resource index is often very very different. Often small channels have a lower resource index than large channels. What we can do now is dimension those so that they have essentially the same resource index. So the two advantages of this approach are, so far, is that we can address this channel churn. We can have a more balanced resource index across channels. The third thing also that this provides is more structured streaming. So within a distribution group, let's even go back here, there's a lot of work on how you should do the distribution within within ISO system. Should you do a push system, pull system, push-pull trees? There's been already 20 papers probably written on that in the world. But in fact, the thing is that when the system is very stable, you can go back to sort of tree-like structures, which have better performance properties. So that's advantage again with FUD here is that since this is very stable, we can use we can optimize the distribution, the scheduling and the routing within the group to improve performance. So that's the third advantage here. If I could just get up there, so that's this structured streaming. Scheduling and routing can be optimized within the stable VUD swarms. So as mentioned here, one of the problems is overhead. And the way we address the overhead is to use substreaming. The more, if you take a channel and you break it up into more and more substreams, you're going to reduce the overhead, because the amount that you download now, how much do you download as a user? You download the video you want to watch, just like you always had to, plus one or more substreams. Suppose you're only designing one substream, and that substream is very thin, then you're not downloading very much more. And so the total amount of upload traffic in these systems is equal to the total amount of download traffic. The total amount of upload traffic across all users is equal to the total amount of download traffic across all users. So by using substreaming and using very thin substreams, you reduce the overhead traffic significantly. And we'll have some figures on that in a few minutes. So that's that there. The other issue is then, how do you go about dimensioning those groups? And in particular, there's still, peer churn here. Peers are still coming and leaving, and some channels are becoming more popular than others over time. So you need to do something intelligent to dimension those groups and in real time. So that's what we're going to talk about a little bit. So the goal is to maximize the resource index across substreams. And you can formulate this as an optimization problem. And this turns out to be a mixed linear integer programming problem, which is, but it's something we wouldn't want to do in practice anyway, because we need to do this in real time. So I'm going to skip over this. So this is what we want to do. So here, how do we create those groups dynamically? How do we maintain those groups? And so the goal, again, what we want to do is we're going to do this with the goal of maximizing the minimum resource index. So each channel or each substream has a resource index. We would like to get all those resource indexes as high as possible, equally high. So we're going to take the minimum. The goal is going to be to minimize to maximize the minimum resource index. And hopefully, in doing so, all of those resource indices will be above 1, significantly above 1. So what do we do here? So let's use the laser pointer here. So when a new peer joins, where do you put that new peer? This is the main method we use to dimension the groups. So when a new peer comes, we look at all the resource indices of all the groups, and we find the one that's the lowest. And we could assign that peer just to that one. So we assign that peer. So the peer joins the resource group for the group that needs it the most. It needs the upload capacity the most. All right, so assign peer to the most resource-poor substream distribution group. And now what we're going to do is we may actually assign it to more than one group. So the peer comes with a certain amount of upload bandwidth available, say 1 megabit per second or 2 megabits per second. And maybe the video rate is 500 kilobits per second. So we can assign it to more than one group. And so I'm going to talk about the algorithm in a second, how we do that. But we may assign it to more than one group.
So you have some kind of like a reserve.
Some kind of reserve?
Yes. For example, like in battle, right? You put some people just wait until you have a new battle. And here, because it's a greedy algorithm, whenever a new peer joins,
right.
And what if you start a new channel, for example?
Right.
Now you have a new problem.
New channel.
Right. Suddenly you have a channel becoming very popular, for example.
Right.
So then the supply-demand ratio would be unbalanced. And now you look around, actually you don't have a reserve.
Uh-huh.
So one way to do is provision each channel to reach a certain provision level, for example.
Right.
1.5, 1.8, whatever. Mm-hmm. And those guys will be reserved. Right. Meaning they are not joining any channel.
Right.
And so because I think one reason actually is flash across. Suddenly one channel becomes popular.
Right.
And you look around and actually you may not have enough arrival to fill in the supply for that particular channel.
Mm-hmm. Okay. Right. No, the reserve is an interesting idea. That's another kind of approach you can be taking. There's many variations, I think. That's an interesting one. So yeah, good. So basically, this approach that we take in this particular simulation, this heuristic that we're using here, but there are other interesting variations, is the following thing. So basically, we're going to just use a water filling policy. Here's the different groups here, and here's the current values of their resource index. And when a new peer arrives, we're going to assign its upload capacity most likely here. but we don't have to sign all of it here. If we sign, a little bit and it brings us up to here, for example, then we might now go ahead and start signing some of its extra upload capacity to this peer over here. So what we're going to do is we're going to allocate, when I arrive, I have a certain amount of upload capacity I bring to the system, and I'm going to first look at the group that needs it the most, allocate some of my resource capacity to that group. If there's still some capacity left, I go to the next group over here and allocate that. And then when I do these allocations, I follow this rule here. This is a detail, we won't worry about that, but there's some number of little rules that we must follow. So that's basically it. Now that doesn't necessarily solve the problem. So even because there might be a flash crowd, like you say, or something going on, or just maybe not an immediate change in popularity of a channel, but a slow change in popularity of a channel. So if the resource index sigma k falls below the threshold, what happens then? So maybe you can't wait for new peers to arrive to repair the problem. You need to repair the problem immediately. So then you're going to have to do something. And what we try to do is the first thing we try to do is shift bandwidth without being reassigned to new substreams. So let me just finish this and I get that. So when I'm in there, I'm typically uploading, the way this is designed, I may be uploading more than one substream, and as part of VUD. So I'm not just uploading one substream, I'm uploading 2, 3, up to 5 substreams. And if I know that one group needs more bandwidth, I can shift some of my bandwidth from a substream that doesn't need it to a substream that does need it. So in this way, in doing that, I don't have to get reassigned to new groups. Everyone can stay in their same group, and so this will keep things a little bit simpler. And we just shift our bandwidth from groups that need it, from groups that don't need it to groups that need it. And I'll get just one last thing. So then there's a third. That might not be enough. There's still some situations where just shifting bandwidth is not enough, and then there are times when we may even need to actually move peers from one group to another. And that's sort of the worst case situation, but that happens as well, and we account for that in our design. Did you have a question?
Yeah, I realized I don't actually understand the resource ratio.
Uh-huh.
So first I thought I understood it. The U's are the capacities of the upload capacities of these things, right? Versus the amount of that they're actually consuming.
Exactly.
But now that you have multiple things going on, I'm not sure I understand. So the U's the upload capacities don't change, right? Or they do?
The upload capacities of peers don't change, but I'm going to take my upload capacity, whatever that is, and I'm going to allocate portions of that to different groups, some different distribution groups.
Okay, it's allocated, not necessarily used. So, for example, if we're just counting the U's as being how much bandwidth we're say UI is the bandwidth that we're actually using to upload out of node I for some.
Right.
Then the resource ratio is going to be identically 1 if that's for all of these different channels, right? If that was the.
That's right. You're right. That's right.
But that's not obviously not the interpretation because you have these different. These resource ratios vary.
Right. Right.
And so they must be the allocated bandwidth for that stream?
It's the allocated, right. The allocated, right.
So is that another problem then? I mean, it used to be that you don't allocate it, you just you have some upload bandwidth.
Right.
And now how are these resource ratios defined really? I mean, what are those used now? I mean, because you're going to have different channels,
right.
You have different use for each channel coming out of a particular node, and you have to allocate them. Like you have a total amount of upload capacity from a particular node,
right?
And you're going to compute resource ratios for each of the channels separately, right?
Right.
So now we're going to somehow have different. We're going to partition that total upload bandwidth into the different channels.
Right.
Those will be the U's for each channel.
Right, exactly.
So how do we do that partitioning? I don't understand.
Huh?
Go ahead.
Well, how do we do with that assignment? So again, like I come in with I'm not sure with 2 megabits per second of bandwidth, and I look at the current resource ratios using and again the resource ratio is defined on how much is allocated, as you say, and I find the group that has the lowest ratio. I find a group, the lowest one maybe is 1.1. Now 1.1 is a dangerous situation to be in. It's still above, even though 1.1 has been allocated, because even though there's 1.1, in theory there's enough to supply, some peers may not have actually the content, and others will. So so you may be missing a lot of chunks. So you want to be at a higher. So the lowest one is 1.1, and so I see, okay, this guy is 1.1. I'm going to give all my bandwidth maybe to him, and all my upload bandwidth that I'm ready to allocate. So now he goes up to 1.3, and he's in a better situation. That group is in a better situation now.
But do the peers have to communicate with each other their allocation?
So right now we're sort of just assuming a centralized design, so that some central controller sees everything. I mean, in future works we may look at some kind of decentralized version, but yeah.
Another thing is, say, suppose you allocate, so a peer allocates, say, 200 kbps for this stream, but it's actually not using, because it's not using that 200 before. So that means that part of the bandwidth cannot be used by others.
It cannot be used by others. That's right. Right.
And that's there, and it depends on whether the system is a pull or push. Right? That's there. There could be, you allocated 200 kbps, but there's not enough pull coming from there, then that resource is wasted.
I guess that's sort of true.
Well, in a sense, it's going to be wasted anyway, right? I mean, just because you allocate it, you're not going to use it. I mean, if the presumption is as a whole system, the whole use will be summed to more than what you're consuming.
Well, I mean, I think in a future paper we could look at some kind of more intelligent scheduling algorithm where you do this allocation, and those allocations are just priorities, and so that if someone else wanted to use that bandwidth when no one else was using it, you could let other channels use that bandwidth, for example, right? But for the time being, we're not doing that. Yeah.
So how do you figure out the upload bandwidth at the beginning?
That you make available?
I mean, how do you know like the UI, the value? Because I think it may change.
How much your UI is? Well, like in BitTorrent, yeah. I mean, like in BitTorrent, right? You can configure in BitTorrent how much your upload bandwidth is going to be, how much upload bandwidth you're going to supply to the BitTorrent application. So that's basically so what's going on here, is that you've configured that value, and that's what you would report to the server. So you report to the sort of centralized controller. Okay.
So what happens if you cannot reach that rate?
Oh, then you won't give it. I mean, I guess those are issues that can be worked on, in a more refined discussion design. But I think roughly is that if you don't contribute all the bandwidth that you still have the overall system measuring how much uploading is going on in the channel and what the demand is. So the system is still measuring the resource index, sigma, for everyone. And if because someone is not contributing as much as they said they are, then you'll just see a lower sigma value than perhaps that you're expecting. And so you have to put more people into that channel. Okay. So here's simulation result. And so this simulation, we basically used a packet level simulator that was developed at Tsinghua University and modified that a bit. And the simulation takes into account channel switching, peer churn, heterogeneous upload bandwidth, packet level transmission, round trip time latency, ZIF-like channel popularity, And we're going to use push-pull scheduling for both ISO and VUD to make this comparison fair. In the simulation, it's a trace-driven simulation. There are 50 channels. Each one has 400 kilobits per second. The 2,000 peers. We use the upload rates that came from a study that was done here at Microsoft a few years ago. The average peer system time is 67 minutes. We just take that. The channel churn that we use follows an IPTV study that was done out of Telefonica a year or so back. So we use the numbers there. Again, we found in that there's a huge amount of channel churn with 70% of the peers staying in there for less than and a channel for less than 10 seconds, if I recall, and 5 substreams per channel. And so just some results here is that here we're looking at popular and unpopular channels for both VUD and ISO, and this is the channel switching delay, and we see that the channel switching delay the channel switching delay is a time to acquire 5 seconds of the new channel, by the way, and we see that the switching delay for VUD tends to be almost always less than 10 seconds. Whereas the switching delay for ISO can be much longer. We have a lot of delays that are over 25, 30 seconds for both the popular and unpopular channels. So we see that VUD does much better in terms of switching delay. Playback lag is a similar kind of thing. We see this is the VUD design here, and this is the playback lag for ISO. And see playback lag for ISO is typically very long, on the order of 15, 20 seconds. It can be long for some peers as well here if you're in VUD, but on average it's much smaller than it is for ISO. Chunk miss ratio, similar kind of thing. This is what we get here for VUD here. The chunk miss ratio is relatively low. This is a situation where the overall resource index is low, so performance is tight, whereas the chunk miss ratio for ISO again is in this particular scenario is very high. It's really unacceptable. And finally, just getting on the overhead from the simulation, we look at a different number of substreams and determine the overhead. Define the overhead as the bandwidth used to upload video to distribution peers divided by the bandwidth used to upload video to the viewing peers. I just burnt out the laser, I guess. And as expected, as you increase the number of substreams, the overhead can drop down. So as we get down to 5, 6 substreams, the overhead is less than 20%. So there's a trade-off here. We are introducing more additional overhead. We need more upload capacity to do this, maybe 20% more upload capacity, but it seems that the advantages outweigh the disadvantages.
Right. I don't fully understand this result. So let's think about it. Overhead, I think, will probably follow. A simple way is, if you know how many substreams you're going to have, let's just focus on one stream. Okay.
One channel?
One substream.
One substream.
Either you have one substream or multiple.
Mm-hmm.
It doesn't matter, right? So let's do a very simple high-level supply-demand analysis.
Okay.
Okay. So therefore, no matter what, because substream, I assume they have to receive all substreams.
Mm-hmm.
So what I would say, so let's look at one substream.
Mm-hmm.
Originally, suppose you have n users in your channel. They all need to supply n units. N multiplied by, essentially, just the accounting will be n receivers. That's n. Suppose
n receivers?
Right.
Want to receive one substream?
Yes. Right. Originally, I'm going to have n people who are going to watch this channel, so therefore you're going to distribute this stream for n times.
Right.
And now the overhead is essentially the size of distribution group.
Mm-hmm.
Because right now, instead of distributing this upstream to end users, suppose we have k distribution nodes.
Mm-hmm.
Now, the total number of users who are going to receive this one would be n plus k.
Mm.
Original was n. Mm-hmm. So therefore, overhead will be k divided by n.
K divided by n?
Yes.
Uh-huh.
Because originally you need to send to
k is
k is number, the size, how many users in the distribution group.
Uh-huh.
So, right. Originally, you need 100 people watching it. Now I need 5 guys to help, so therefore I'm delivering to 105. My overhead 5 divided by 100.
Right.
So given this analysis, I don't understand why it's even related with substream number. Of substream.
I think the way to look at it is that the amount of upload capacity is used is equal to, the aggregate amount of upload capacity is used is equal to the total amount of download capacity that's used. The download capacity that's used, right, is how much is being used. Is everyone needs, and for the overhead, is that we're downloading now just, rather than a whole channel, we're downloading just a substream to redistribute. And so if we can make that substream thinner, the amount that we're downloading, the aggregate amount we're downloading is less, and therefore the aggregate amount that we're uploading is less. Yeah. But this is a tricky issue. We have actually worked that out in the first paper. Maybe maybe we can talk about that a little later. Sure. Yeah. Okay. Yeah.
Look at the
right.
second paper.
Right.
Probably.
Yeah, we'll get into that. Okay. So now this one is more on how much time do we have here?
We have a total of 1.5 hours. We have 40 minutes left.
I don't want to bore everyone too much, but so we have queuing models so this is the second paper. This is a little bit more mathematical. So our goal is to, but not very mathematical, it's very simple math actually. So the goal is to develop analytical framework for multi-channel live video streaming systems. So so that apply both to ISO, what we were just talking about, and VUD. And then the other thing we want to do is once we have this analytical framework, we want to use it to optimize VUD performance. We like to use it to, for example, to dimension those VUD groups. And in this discussion, we're going to use the following performance measure a lot. It doesn't have to be this measure. There are other ones that could be used that are also tractable, but just to keep things simple, we're going to use this one here. And it's what we call the probability of universal streaming. And that's the fraction of time the resource index is greater than 1 for all channels. So again, we want that resource index is sigma. We said if sigma is greater than 1, typically a channel has good performance. And so we want to now look at the fraction of time that all the channels are happy. Every single channel has a resource index as 1. Maybe that happens 10% of the time, 20% of the time. If it happens 20% of the time, then our probability universal streaming is 0.2. If it happens 90% of the time, it's 0.9. Okay, so that's what we're going to focus on here. So here's this very simple queuing network model of the system. We're going to view each channel as a queue and view each viewer as a customer. So customers are going from one queue to another because they're changing channels. And when a viewer changes channels, it's going to be routed to a new queue. And so we assume that there's some kind of matrix out there, switching matrix, which is given over here. This is the probability that a user goes from channel I to channel J. And so customers move about, customers don't interfere with each other, obviously, as they move from channel to channel. If I change channels, that's not going to have any impact on whether Jin changes channels. And so because of that, you naturally use an infinite server queue at each queue here. And then let's let 1 over mu j denote the average sojourn time. Now, since we have infinite server queues, there's this so-called insensitivity property from queuing theory, which says that we can have any distribution we want for the sojourn time. So we're not limited to exponential distribution. We can use an arbitrary distribution as part of here. So we're not assuming anything about the distribution of the amount of time that someone spends in a channel. But let's just let 1 over mu j denote the average time you spend in a channel. So this is a classic queuing model. I don't know how many of you studied queuing theory, but when I was a PhD student back in the old days, that was like one of the main things that they were always teaching was queuing networks. And now it's sort of gone out of fashion a little bit, but it turns out that it's very useful here, and it's not a real stretch to use it either. It's a very natural model. It's not like we're trying to put a square hole, a round peg into a square hole. It actually is the right model for this situation. So once you have that, then you can actually okay, so the first thing you have is that this very standard result is that the probability that there are M1 users watching channel 1 and M2 users watching channel 2 and MJ users using channel J is given by this expression here. And here we're going to look at it, first of all, in a closed setting, closed queuing network. So assuming here there's no peer churn. It's that the peers come and they stay in the system forever for the time being. We're going to look at when there is peer churn as well, but peers stay in the system, but there's channel churn. So this would be a situation in a model, for example, a set-top box environment. So you have this whole thing running out of set-top boxes, which are always on. So there'd be no peer churn. There'd only be channel churn. And so n is the number of peers. Rho I is lambda j times mu j. So 1 over mu j again is the average sojourn time in channel j. Lambda j is what you get from the traffic equation, the standard thing that you get from queuing theory in the traffic equation. So that's a well-known result from Jackson networks. And so everything is pretty straightforward. Once you for a case of when you have peer churn, then we'd use an open queuing model. And so there, peers would arrive at some constant rate and join a channel J with probability P0J. There's a new traffic equation. That's the standard equation that's used for open queuing networks. You get a new value of rho J accordingly, and you get a slightly different formula. In this talk, we're going to talk about the closed queuing case. The whole analysis goes through for the open queuing case as well. So you can definitely handle peer churn. But we're going to look at the closed case when there's no peer churn, just for illustrative purposes here. So given that now, we're going to go ahead and do some analysis. And it's very, very straightforward analysis we'll see here. So first thing we want to ask is, the goal is we want to determine the probability of universal streaming. We said the probability of universal streaming is the probability that every channel is happy. Okay? And we're going to do this for the case of VUD initially. And so what is this quantity here? This is the resource index for channel J substream S, S substream in channel J. And MJ is a random variable. It's the number of users watching channel J. That has this distribution over here that we could derive from over here. So this is the resource index for channel J, and of course it's random because the number of users watching channel J is random. We want that to be greater than 1 for all substreams in channel J for all channels. If that is the case, if this is greater than 1 for every single substream, then we have universal streaming. So we want to calculate that probability. That's the measure we're using here. There are other measures that are possible. So it's the probability of universal streaming. So again, the resource index, just go back up here, for channel J is given by this formula. Again, this is the number of users watching channel J. This is channel J's substream S. This is the rate of substream S. And this is the amount of bandwidth that's been allocated to that substream. This is the amount of bandwidth that's coming from the server. And this is the amount of bandwidth that we're getting from each of the users that have been assigned to substream S in channel J. And this here is the rate that is being taken away because this is the rate that's being taken away because there's some users watching this. This is the number of users watching substream S, and this is the rate at which they're watching it. So that's the sigma j there, and so one assumption that we're making here, just that we're assuming for the time being in this analysis, just to make things simple, that a user allocates all its bandwidth to one of the substreams. So we don't break up our bandwidth among multiple substreams. We allocate all our bandwidth to one substream in this in this analysis here. Okay, so that's the thing. And now, so then you can go ahead then, and since you have an explicit equation for the joint distribution of MJ from a Jackson network, you can go ahead and calculate this probability, and the probability looks like something like this. And then that is the kind of thing, like if you look in the literature and loss networks and queuing networks, people wrote dozens of papers on that, on how to calculate that efficiently. Okay, so you can just use that if you want. And sigma j is given by this expression here. So it's all very straightforward type of stuff. So the thing is that once you have this kind of queuing and loss network model, what you can go ahead and do, you don't have to reinvent the wheel. You can just go into the literature and start reusing, not exactly, you have to modify things a little bit, but not a lot, and you can crank out all kinds of nice results. And that's really basically what the paper was about, was going back to the old literature and just applying it to this kind of context here. Yeah.
I just want to check my understanding. So if you know the number of people watching a particular, I guess substream channel, substream, then you can compute sigma. I mean, so the sigma, the equation on the top is just a function of, all the other numbers besides m are
constants, exactly. Right.
Okay.
All the other numbers are constants.
Depend on m.
Don't depend on n. So here what we've done here is we're doing VUD, and we're assuming now that we have assigned, we have a fixed number of peers in the system, n, and we have assigned each peer to a particular VUD group. Fixed for the time being. Yeah. Right. And each peer gets assigned to exactly one VUD group.
Okay.
Yeah. Okay? And so that's and so the groups are determined here. So NJS is a set of peers that have been assigned to channel the substream, the group substream S channel J. Okay? All right. So so one thing we can do, for example, is an asymptotic analysis of VUD. So if you look at the literature that things like Frank Kelly did on loss networks back in the 90s, where what he did is he studied loss networks, which are like circuit switch telephone networks, and there's a product form solution there. And then what you can do is that he looked at what happens when those loss networks get larger and larger, do things simplify. So we tried to do something similar to that, and came up with a theory that works out nicely here. So here, for example, we fix the number of channels. The number of channels are fixed, and we let the number of peers go to infinity, so get larger and larger. So we're going to look at bigger and bigger systems. And for simplicity, we're going to assume there's no substreaming. You can do this for substreaming, but just to make it simple, suppose there's no substreaming. And we're going to look at an asymptotic regime. What we're going to do is this is the number of peers that we assign to channel J. And the number of peers we assign to channel J is going to be proportional to the total number of peers in the system according to some fixed ratio here, factor kj. So k sub j, which is going to be fixed in this model here, is the relative number of peers, or the fraction of peers that have been assigned to channel J, so channel J for distribution. So the question is then for a large system, how should we set kj? We'd like to know how big each of our VUD groups should be. Can we come up with a simple formula that tells us what should be the relative number of peers we assign to channel J? So that's one thing we're looking at here. So I'm not going to go through the proof. It's not that hard, actually. But it turns out that, let's look first at the case of the homogeneous case when each upload rate is the same. It turns out there's this critical parameter called alpha, which is given explicitly by this formula. What is this formula? Rj is the rate of channel J. Rho j is essentially the utilization of channel J. It's the lambda j divided by mu j. U is the upload capacity of a peer. And Rj is the rate of a peer. The rate of channel J. And the theorem says that if alpha is greater than 1, then the probability of universal streaming goes to 0. That as the system gets larger, the universal streaming goes to 0. There's you're not going to have good performance if alpha is greater than 1. On the other hand, if alpha is less than 1, then if you set the kj's equal to this particular value here, and there's other, but this value here, rj times rho j divided by this, then the probability of universal streaming goes to 1. So there's this, like, alpha provides this kind of threshold here, this dichotomy, where if alpha is greater than 1, there's nothing you can do, you have bad performance. If alpha is less than 1, you can have good performance if you set if you dimension properly, is the fraction of peers that you put into channel J is given by this value over here. So that's just kind of results that you can get from this queuing analysis. Then if you look at a somewhat more interesting cases where you have heterogeneous peer types, where you have some that have low rate, UL, and some that have high rate, UH, can you still find how to dimension the system? And so let's suppose the fraction of low rate peers is F, that's given. And again, you have these two rates. How do we find the optimal allocation? So KJL would be the fraction of low rate peers you put into channel J, and KJH is a fraction of high bandwidth peers you put into channel J. And then what you can do is you can formulate this linear program here, where A to J's are given. These are just, I didn't put them here, but they're given constants that come from the basic data of the system. I didn't bother to write it here. And these are the variables, the KJs, and you can solve this simple linear program. This is a relatively easy linear program to solve. I mean, you still can't solve it by hand generally, but you only have 2 times J variables here, and not very many equations, obviously. And turns out that if the value of this linear program is less than 0, then you can prove that the probability of universal streaming goes to 0 as the system gets very large. And if the value is greater than 1, then the probability of universal streaming goes to 1, and the KJs you're going to use are the optimal solutions. So the amount of peers you're going to put into each group, high and low bandwidth peers, are given by the solution to this equation. Okay. Now, if you want to do analysis of ISO, then you still have those MJs. And it's the same expression for the MJ is the number of peers watching channel J. That has nothing to do with the design. That's just user behavior that determines how many peers are watching channel J. And so the probability of universal streaming is given by this expression. Now, what is this here? Script MJ, that's the set of peers that are currently watching channel J. Okay, so the amount of, this is ISO now, it's not FUD anymore. So the amount of bandwidth that's being provided to channel J is the amount of bandwidth that's coming from the server plus the amount of bandwidth that's coming from the set of peers that are watching channel J. Because if you're watching channel J, then you're providing all your bandwidth to channel J. So that's the amount of bandwidth the upload bandwidth that you're providing to channel J. And this is the demand for channel J, the number of peers watching channel J times the rate of channel J. And so in order to get this, basically, if this is greater than this, and sigma is greater than 1 for that channel, and you need that to hold for all the channels. So that's the probability of universal streaming for the traditional isolated design. Once again, you have this thing here. Now, this is more difficult to solve, right? In the VUD, actually, it turns out in the case in the VUD case, you have this nice little formula if you wanted to. You can go ahead and solve this using standard convolution algorithms very quickly. Here, you don't have anything like that. But because of the special structure, you could use Monte Carlo important sampling methods to rapidly solve that if you wanted to. And again, that kind of thing has been looked at in the queuing literature. So for the asymptotic analysis, there's a critical value as well for ISO. It's even easier to derive. It's given by this expression. And once again, if alpha is less than 1, then probability of universal streaming goes to 0. So now what we could do is we could compare, for example, in the asymptotic case, VUD and ISO, using those analysis. And this is just an example here where we have heterogeneous bandwidth. The high bandwidth peers have a rate of 4R, and the low bandwidth peers have a rate of 2R. there's two types of streams in there. One stream has a rate of 5R. One video channel has a rate of 5R. Another one has a rate of R. I guess there's just two channels in this. Yeah, in this example, there's just and channel 1 has a row value of 0.2. Channel 2 has a row value of 0.8. And you can easily go through the calculation. In this case, ISO has an alpha value that's greater than 1. That means that the probability of universal streaming will go to 0 in this particular case. And in VUD, what you can do the allocation so that the alpha in this case is less than 1. So in theory you can do the allocation so probability of universal streaming goes to 1. And in fact you can do those allocations. So just this little example there. So any questions about any of this at this point here? Any of this kind of stuff? Yeah. Okay. So, yeah.
Can you say, going back to the simple, there's only one rate case.
Okay.
Can you give an interpretation for the allocation?
That's a good question. I don't know if I can. I'm trying to find it here. Here it is.
Yeah.
Alpha here is just sort of the excess. So I wouldn't worry about that too much. Alpha here is less than 1. So, but okay. So anyway, but just some interpretation here is that one thing we see is that Kj is proportional to rho j. Rho j is the popularity of the channel. It can be viewed as the popularity of the channel, the relative popularity of the channel. Rho j is actually the expected number. It's the fraction of peers, right, that are watching channel J, on average. Okay, so the more peers that are watching, so that's fairly intuitive. That the more peers watching channel J, the bigger we need to have the distribution group. The second thing, it's also obviously we have this RJ here in there, so that is, but it's not quite proportional because we also have RJ down here. But as you would expect, as the streaming rate becomes larger and larger for that channel, then you would want to have more peers in that channel to distribute there. Because each peer is contributing the same amount of upload capacity U in this homogeneous case. And finally, I guess, let's see, how should we interpret this? U minus Rj term there. And
my interpretation is this.
Right.
I mean, generally in this assignment, you may not be actually assigning the peer, which is watching the channel,
right,
to that channel.
Exactly.
So if that's an alignment, or I mean, let's say you align everything wrong, you are wasting Rj for each of the peer you align that way. Because I mean, that peer doesn't need that basically channel J, but you are downloading it anyway.
So when you're doing the ISO analysis for a single upload rate, uniform upload rate, does it reduce to this thing without the RJ on the bottom? Or is
well, in the ISO analysis, you don't do any assignments there, right? So there's no notion of KJ in ISO. In ISO, yeah.
You don't have any waste.
Okay, maybe what I mean then is that sort of the alpha then, in the critical parameter.
The critical parameter, okay, let's take a look at that. Yeah.
So here you kind of, okay, let's say UL and UH are the same.
Right. So that becomes just U.
Okay.
Right.
Okay,
right, yeah, so it's very intuitive there.
Okay.
Yeah. So basically what we're saying in the ISO case is that the maximum rate has to be less than the upload rate of a link, right? In order for that to work there. So that's very easy to derive in that case. Yeah.
I think basically if I try to interpret, so please can you go back to the
sure.
slide that basically if you just mentioned.
Let's see, oh, this one here.
Yeah. So my interpretation is this. Each this Rj, rho j divided by U minus Rj is a kind of supply and demand factor for each individual channels. The demand is RG times rho G. Basically, rate of the channel times the popularity of the channel. The supply is U minus RG. How much rate available minus the redundant rate you taking in. Now, the sigma of over all the channel, which derives the alpha, is the forgiveness factor for all the systems. Basically, in each channels, you have basically some oversupply and undersupplies, which says, okay, how much resource you should allocate more to each channel. But I mean, if you look at overall the systems, alpha is the value which gives you whether your system is oversupply or over demand.
That's right.
That may be basically, I mean, well, you need the mean
So in the previous paper, you mentioned that if you have more substreams, then you have lower overhead.
Right.
In this model, you only assume no substream, just one substream.
Right.
So if that's true, then if you have more substreams here, then actually your equation can be changed.
Equation will change, right? A bit.
This alpha.
Right. That's right. Yeah, and I think in the paper we actually created an extended version of the paper for journal submission. We do it for the substreaming case there. Go ahead. I'm sorry.
And then suppose you have infinite number of substreams.
Right.
And will that this equation finally evolves to U minus Rj becomes U minus 0.
Right.
Is that true?
It's a good point. I think it is true actually. That's correct. Yeah, that should be the case. Okay, so but what this little example here shows that even though when you're not using substreams, even in the case when you're not using substreams, there are still situations where there are some natural situations where VUD is even going to do better than ISO there. That even with the additional overhead that VUD brings, you still have better performance with VUD. And why is that? Is because VUD is handling the channel switching a lot better than ISO is.
Actually, for example, you're going to have, for the ISO case, you're always going to have PS go always 0. It's not goes to 0. Because for channel 1, your demand 5R. The upper supply ratio is 4, so therefore channel 1 can never support itself anyway.
Right, so it's 0 always. It doesn't go to 0, right. It's always 0. Right, PS is 0 for all cases, right? I mean, this is, it's an illustrative example here, right? Yeah.
Basically, in that case, stream 2, PS is always 1, right? Even basically.
Yeah, because the supply 2R, demand only R, can always support. So that's particularly mean you shuffle the resource a little bit.
Right. Right. So VUD offers that flexibility to be able to shuffle resources to meet the demand. Okay. So now some more numerical results here very quickly. These results are not simulations. These are all results that have been calculated from the queuing model here. If we can look at much bigger systems, so we have 1,800 peers, 20 channels. We have two classes of links here, upload rates, 0.2R and 3R. We're assuming that every video is at rate R in this situation here. So we have some that can upload at 3 times video rate and some that can only upload at 20% of the video rate. And we use this asymptotic heuristic to dimension the substream swarms. And so here's this is a plot where now we're looking at the probability of universal streaming versus a ZIF parameter. So we assume popularity follows a ZIF distribution. And what we're seeing here, VUD versus ISO in that example, as you increase the ZIF parameter, then you increase the number of small channels. And the problem with ISO, with small channels, is that you very often have a resource index that's lower than 1. Why is that, do you think? So a small channel with ISO, small channel means you may have like 2 or 3 users, the resource index can go below 1 because what we're having here is that the channel is going to be composed of these high bandwidth and low bandwidth peers. And in a small channel, in a large channel, there's a law of large number effect, where so that if you have all these the peers joining randomly, and on average, the amount of resources that they contribute will be greater than the demand. But in a small channel, very often you're going to have the resources contributed will not meet the demand. So that's why small channels are a particular problem for the ISO design. Whereas for VUD, because we're dimensioning to handle those small channels to some extent, so when we use that heuristic, we still have some drop off here with the small channels, but we don't have we have performance on the whole that's much better. So the probability of universal streaming we see is much better in this example here. Here now what we're looking at is the probability of having a resource index greater than 1 for each individual channel when using a ZIF parameter set to 1. So ZIF parameter is now set to 1, and we're looking at the channel IDs here, ranging from 2 to 20. And so these are the biggest channels, the most popular channels to the least most popular channels. And once again, we're seeing that for ISO, for these smaller channels, the ones that are less popular, we have they might have, for example, a probability of the probability that sigma is greater than 1 is only 80%, whereas for VUD, we see that it's very high consistently. Very quickly here is one actual additional refinement that one can do to get even better performance. It's it's just a heuristic, but it's a very simple idea. So now what we like to do is try to get the probability that the resource index is greater than 1 to be the same for all channels or all substreams. So we're going to develop a heuristic now to get it to be so that we make each channel of equal importance. The channels that are popular and channels that are unpopular. And in this heuristic, we're just going to assume a normal distribution for mj. So we're going to solve this equation. Rather than using the distribution that comes from the product form solution, we're going to use a normal distribution, which is the actual distribution is binomial. This is going to approximate the binomial. And just for the time being, let's assume that all stream rates are. When you do that, you get this following closed form solution for how you should dimension all the VUD groups. So channel J, substream S for, this is the number of high bandwidth peers that you should put in channel J, substream F. This number of low bandwidth peers you should put in there. You get these closed form solutions here using this normal distribution. And when you do that, we get now, this is what we get for ISO. This is what we get for VUD using that asymptotic heuristic. And this is what we get using this new heuristic, where you get very, very solid performance. Even for the unpopular channels, the probability of universal streaming is essentially 1 using that heuristic. So that's just sort of nice. So that's, just in conclusion then, what this stream of research was about was, first of all, sort of identifying that in addition to peer churn, there's channel churn, which happens at a much higher scale, and then try to, and also taking notice that among channels, there's typically a very large resource imbalance across channels, and so try to design a new kind of P2P live video streaming design that takes into account this channel churn. And so that was the first half of the talk. And the second half of the talk was about developing some simple mathematical models that can be useful for modeling both the ISO design and the VUD design. And so I want to thank everyone again for your excellent questions and comments. If you have more, we can do it now or later.
You have an excellent talk. It's very Any questions from the audience?
Yeah, I have a question, probably related to practical application or software running on the internet. So at least when I was talking with a live stream application, those developers, they tend to their thought was even the unpopular channels may suffer when the peers switch into popular channels. They don't worry too much about unpopular channels because this is not they're they don't put much effort on that unpopular channels, but they worry a lot more on their popular channels serving a lot of people online. But so in your solution, I feel that you're trying to somehow switch or use those some extra capacity of those popular channels to serve the unpopular channels.
Right.
So
to some extent.
Yeah. So I mean, do you have any indication or evidence that a real system will have that motivation to support it?
Well, I think if you look at for example, we've done a different study on BitTorrent recently, and in BitTorrent it turns out that it has a very thick tail. For example, there's a lot of people downloading videos, and the swarms are very small. There's some swarms that are big, like 10,000, 20,000 people, but the vast majority of the swarms, like 90% of the swarms, have fewer than 10 users in them. And so again, I guess it could be most likely in these systems, in the long run, probably going to expect to see a lot of small channels in there. And now, this is a very competitive business. Bao Chen and Lee were talking about, he knows he works with some of the companies out there, so he knows this better than anyone. But I'm trying to convince him how important this is. But there's all these companies in there, right, in China, right? If this is another way that one can distinguish themselves from one company can distinguish from another by saying that we support small channels, we have lower switching delays, we have smaller lag, it's one possibility, right? Now, I'm just going to say I had a very interesting discussion about Chen. The point that he made, I agree, is that he's being very quiet because I'll say some of the things. He's very polite, but his argument would be, well, those companies. For one thing, live streaming is not their main concern right now. Their main concern is video on demand. There's much more action happening in video on demand than in live streaming. That's probably true. And they're less concerned about perhaps improving live streaming, which more or less works. I mean, it's possible that they could get some additional improvements using this or something else, but really their focus is more on demand, since that's really the more killer of the applications. What we're seeing, though, in the literature and Infocom and elsewhere is a lot of focus on live streaming. One reason why is this because it's intellectually interesting. I personally think it's more interesting than the video on demand stuff. But yeah, anyway. Okay. I don't know if I paraphrased. Did I paraphrase your comments properly, or?
There are other reasons.
Other reasons, too.
More technical ones.
Okay.
The demand of
sure.
is important.
Right.
Another small comment is that it seems like when people watch, say, TV online, initially they switch between different channels, but there will be a period of time when they stay there for a long time.
Right.
It seems like for that kind of users, we can switch from this channel-based, basically your method, back into the old method.
Right. We've been looking at that, actually, exactly that, too. So we've sketched out some designs for that. I'm not sure if we're going to write a paper on it. But we sketched out some. In the end, it's just not that. But yeah, it's true. It's something that one can do. It could get better efficiency. Yeah.
Okay. Let's end the talk. If you need to further talk to Keith or discuss with him, he's on the second floor. I think office 2957. 75. Sorry, 2975. Let's thank for Keith again.